Today we're going to speak about thermocouples. Now, if you happen to do temperature measurement, this is possibly one of the most important measurements that you are going to take in your plant. Again, I'm going to ask that you don't be fooled by the image of a thermocouple if you were to take it out of the store. As you can see, compared to the video that we did the other day on the RTD, they're going to look very, very much the same, but there is a difference. So make sure you do take out the right device. Thermocouples work on the Seebeck effect, and that is where two dissimilar metals generate a voltage that is proportional to the temperature. If you look at my sketch, you can see that we have got metal 1 and we have got metal 2. Those two metals are going to generate a voltage. So when two different metals are joined at the end, they're going to form a sensing system, and it is this system which we are going to use to measure the temperature. Now, if you look at the sketch, you actually can see that they are going to compare the hot junction to a reference junction, and that is where our temperature is going to be generated in a millivolt signal. As a matter of interest, thermocouples are going to have a positive temperature coefficient. They are non-linear devices, and as the temperature goes up, so we're going to find that the reading that we take, which is going to be a millivolt reading, is also going to go up. The temperature goes up and the millivolt reading goes up. Very similar to the RTDs. In the case of the RTDs, also a positive temperature coefficient, but this is going to be a linear device. Again, as the temperature goes up, so our reading, which will be in ohms, is going to go up as well. The modern thermocouples would make use of electronic compensation to compensate for the ambient temperature as well as the temperature at the terminals. Now, the thermocouple itself is going to produce an exceptionally small signal. We speak in terms of a millivolt signal, and it is that signal that needs to be amplified as well as linearized. You can imagine the problems that can be encountered as far as electrical noise is concerned. I will be doing a whole complete section on electrical noise. Please note that the thermocouples are actually going to respond quite quickly because of the fact that they're going to have a very low thermal mass. This is where a lot of people get it wrong. The thermocouple reading is not the temperature that you get out in the field. It is going to be the difference in temperature between what you are measuring out in the field as well as the point of measurement. Let's go and write that down as the delta temperature. Many people that work with thermocouples think that they can just take the reading and that is what they are going to get. Now, that's completely inaccurate. And if you do attend one of my workshops, we will do a number of calculations where you can see exactly how to do the calculation. Different types of thermocouples can be used. We can get the type J, type K, type E, type N, type R, type S, type B. They're all just going to have different combinations of metals that are put together, and that is going to provide us with the different types of temperature ranges that we can encounter. Just as a matter of interest, the type K is the most common general purpose thermocouple that we can go and encounter because of its wide range as well as its durability. Noble metal thermocouples such as type R and type S are used for extremely high temperatures, which you possibly could encounter in a furnace as well as a kiln. The thermocouples are rugged, inexpensive, and ideal for harsh environments. RTDs are still going to be the most accurate device that we can get, but we are going to use the thermocouples for the high temperature as well as high vibration applications. On the screen in front of you, you can see a typical table for a thermocouple, in this case a type J. And all that I want to put forward at this point in time is if you were to go and measure a voltage from the thermocouple such as 3.275 millivolts. Now that does not tell you that it is 63 degrees Celsius. That is going to be incorrect. So what you need to do is you need to have a look at what the ambient temperature is, get the ambient temperature's voltage, and you'll use that in conjunction with this voltage, and that will give you the temperature that you are measuring out in the field. So please be very careful. Many instrumentation people do get this wrong. With an RTD, what you see on the table is what you get. With a thermocouple, you need to do that compensation. With the modern day thermocouples, the compensation is automatically done for you in the instrument that will measure the values. In the old days, this was not the case, and that's why you would have seen people talk about an ice bath or a cold junction reference. Another thermocouple would have been taken, put into the cold junction reference or the ice bath, and that would allow us to compensate for the ambient temperature. Today, all done automatically, but in the old days, it was a separate function. Can we put thermocouples in parallel with each other? Yes, we can, and that will give you a very good average. You might, for example, have a furnace and you'd have 4 of the same thermocouples spaced out around your furnace, and that will allow you to take a nice average temperature. We have said that thermocouples provide us with a very small signal, a millivolt signal, and if we are going to send that over long distances, we're going to encounter all sorts of problems. Now, a thermocouple is made up of 2 dissimilar metals, and the type of thermocouple is going to specify what that is going to be. Now, in the case of an extension cable, my cable can be made up of exactly the same metal that has been used in the thermocouple itself. So as you can see at the top, we're going to have metal A, and we can use metal A as part of the extension cable, and then we're going to have metal B, and we can use metal B as part of that extension cable. Some of these metals are very expensive. You can, for example, go and have a look at the price of platinum or the price of rhodium, and imagine how much that's going to cost you in a cable. So it is the most accurate option that you can go and get, but it's not always cost effective. In some cases, what people will do is the cable itself may just have copper in both conductors, and then it's going to be known as a compensating cable. And this is a very viable option over short distances or with applications where you don't need to have a great deal of accuracy. In conclusion, please note that thermocouples may drift over time due to oxidation or the contamination of the metals. Feel free to join us for many other webinars that will follow this one. Thank you.